Seventh class of electrical drives and control for automation. Seventh class. So in this class we are going to discuss about armature reaction. We know that in a DC generator there are two main parts, stator and rotor. Stator consists of field system and rotor consists of armature winding. Field system produces the magnetic flux. That flux cuts the armature winding of the rotor and an EMF is induced in the armature. So armature is the important topic of a DC generator. So what is maybe armature reaction? Simply we can say it is the effect of armature flux on main flux. So I told you there are two windings in a DC generator, armature winding and field winding. Field winding produces the main flux. Field winding produces the main flux. So when a generator is loaded, load current is flowing through the armature winding. When load increases, armature current increases. When load decreases, armature current decreases. So this armature current can create a flux. Thus there are two fluxes. Flux produced by field winding, that is main flux. Flux produced by armature winding, that is armature flux. It is the armature reaction is the effect of armature flux on main flux. Armature flux disturbances the main flux. That phenomenon is nothing but armature reaction. I am repeating, in a DC generator there are two windings, armature winding and field winding. The main function of the field winding is to produce the main flux. That is the main flux. The main flux is produced by the field winding of the DC generator. Main flux is produced by field winding of the DC generator, represented as main flux. So under no load condition there is only one flux in the DC generator. It is nothing but the main flux produced by field winding. But when the generator is loaded, what happening is the load current is flowing through the armature. When load increases, armature current increases. When load decreases, armature current decreases. Anyway, when the generator is loaded, a current is flowing through the armature. That current can produce a flux. That flux is known as armature flux, denoted as phi A, armature flux. The other flux is known as phi M, main flux. Sometimes it is denoted as phi 1, phi 2. Main flux phi 1, armature flux phi 2, or main flux phi M, armature flux phi 8. It is your choice. So flux produced by the field winding is main flux. Flux produced by the armature winding is armature flux. Armature flux is produced only when the generator is loaded. When there is no load, there is no current flow through the armature. Therefore, there is no flux produced by the armature. This armature flux disturbances the main flux. It is the effect of armature reaction. So what is meant by armature reaction? Define armature reaction. It's a 1 mark question. Armature reaction means it is the effect of armature flux on main flux. It is the effect of armature flux on main flux. Okay. So what is the resultant of this effect that we are going to discuss? So look at the slide. In a DC machine, flux produced due to the main poles or field winding is called main flux. Field winding is provided in the stator of the DC generator. Field winding is provided in the stator of the DC generator. In the construction details of a DC generator, we studied that stator consists of magnetic poles. It consists of a field pole, pole body, field winding and pole shoe, etc. Anyway, study all those things. In a DC machine, flux produced due to the main pole is called main flux. Current flow through the armature conductors also creates a magnetic flux called armature flux. So I am reminding you that this flux is produced only when the generator is loaded. Okay. That armature flux weakens and distorts. It weakens and distorts the flux coming from the main flux. That is, armature flux distorts and weakens the main flux. That phenomenon is known as armature reaction. The action of field weakening and distortion of main flux by the armature flux is called armature reaction. In short, we can say armature reaction means it is the effect of armature flux on main flux. It has two different effects. It distorts the main flux, it weakens the main flux. It distorts, അതിനെ ശല്യപ്പെടുത്തുന്നു, അതിനെ ശക്തി കുറയ്ക്കുന്നു, അതിനെ ശല്യപ്പെടുത്തുന്നു. Okay, it is the effect of armature reaction, is the effect of armature flux on main flux. Then we can conclude those 2 points, distortion and weakening. It weakens or demagnetizes the main flux. It demagnetizes the main flux, and hence the resultant flux is decreasing and induced EMF decreases. This effect is known as demagnetizing effect. So armature reaction, first of all you have to study what is meant by armature reaction. Armature reaction means it is the effect of armature flux on main flux. Armature flux distorts and weakens the main flux. If it is weakening the main flux, that effect is known as demagnetizing effect. Demagnetizing effect means it demagnetizes. That means it weakens the main flux. And it distorts the main flux also, known as cross magnetizing effect. It distorts or cross magnetizes the main flux, which produce sparking at the brushes. Okay, if the sparking is more, definitely our machine will burn. If the sparking is more, definitely our machine will burn. So from this explanation you have to understand one important thing. Effect of armature reaction is very important as far as the life of a DC generator. So armature reaction is the effect of armature flux on main flux. It distorts or weakens the main flux. If it weakens the main flux, that effect is known as demagnetizing effect. Its resultant is the generated EMF is increasing. Why? The flux is decreasing, resultant flux is decreasing. This decreased flux cuts the armature winding and decreased EMF is generated in the armature. Due to demagnetizing effect, generated EMF decreases. And the second, what is the second effect of armature reaction? It distorts the main flux. It distorts the main flux. That means it cross magnetizes the main flux, and therefore sparking is produced at the brushes. So both are adversing effect, both are disadvantages. Demagnetizing effect decreases the generated EMF. Due to cross magnetizing effect, sparking will be there. So both are harmful for a DC generator. It should be avoided at any cost. But we cannot fully avoid this armature reaction. So we can minimize the effect of the armature reaction. How? That we are going to discuss. So one important thing, only 2 points we discussed till now. What is meant by armature reaction? In a DC generator there are 2 windings, armature winding and field winding. The function of the field windings to produce the flux, that is main flux. When the generator is under no load condition, there is no current flow through the armature, so no armature flux. So there is no question of armature reaction under no load condition. But when a generator is loaded, load current is flowing through the armature. That armature current can produce some flux, represented as armature flux phi A. This armature flux distorts or weakens the main flux. Okay, if it weakens the main flux, it is demagnetizing effect. Due to this demagnetization, generated EMF in the generator decreases. What about the second effect? It cross magnetizes, distorts or cross magnetizes the main flux. Due to this, a sparking is produced at the brushes. Anyway, both are harmful to our DC generator. Okay, so armature reaction means it is the effect of armature flux on main flux. So what is meant by armature reaction phenomenon? The phenomenon of armature reaction in a DC generator is shown in the above figure. What is the above figure? Only one pole is shown for clarity. When the generator is on no load, a small current flowing in the armature does not appreciably affect the main flux phi 1 coming from the main poles as shown in figure 1. What does it mean? So look at the figure 1. So there are 3 figures, figure 1, figure 2 and figure 3. So when the generator is no load, a low current or very low current is flowing through the armature. That can produce a very low armature flux. It doesn't create any problem to the main flux. So there is no question of armature reaction under no load condition. Okay, the flux produced by field winding of the machine is represented as main flux. In this case it is denoted as phi 1. Only phi 1 is there. In figure 1 only phi 1 is there because generator is under no load condition. Low current is flowing through the armature. So low armature flux, this weak armature flux cannot create any problem to the main flux. So there is no question of armature reaction as far as figure 1 is concerned. Only one flux is there. The other flux, that means armature flux, we can avoid it because it is negligibly small. Now under no load condition, so there is no load current. Even under no load condition, a small current is flowing through the armature, which is very low, and that low armature current can produce a weak flux. Okay, so this weak flux cannot produce any problem to the field, main flux. So only phi 1 is actually only phi 1 is there. The flux produced by field system here in this slide, it is denoted as phi 1. Only phi 1 is there. That is figure 1. So what about figure 2? When generator is loaded, the current flowing through the armature conductor sets up armature flux phi 2 as shown in figure. By superimposing the main flux phi 1 and armature flux phi 2, we get the resultant flux phi 3 as shown in figure 3. That means in figure 1 there is only phi 1, that under no load condition. In figure 2 there is only phi 2. Such a condition doesn't arise. So imagine that there is only armature current. Practically such a case is not possible because main flux is always is there. There is always main flux in a DC generator. So we can imagine that there is only armature flux for some time. It is not possible at any cost. So flux produced by the armature is phi 2. Flux produced by the main field winding is main flux phi 1. So in figure 1 there is only phi 1. In figure 2 there is only phi 2. This phi 2 disturbances the main flux phi 1. Then what is happening? So that is in figure 3. That is phi 3. So phi 1, phi 2, phi 3. Figure 1, figure 2, figure 3. So look at the figure. Figure 1, no load condition. Only main flux is there. Say a small armature current is there. A small armature flux is there. Because of this armature flux is very low, we can avoid it. We can neglect it. What about figure 2? Figure 2 means, so imagine there is only main flux. Imagination is only possible in this case because there is always phi 1 in a generator. There is always phi 1 in a generator. Main flux is always there. So for some time we can imagine that suppose there is only armature flux. So what would be the condition of the flux? Look at the figure. Only phi 2 is there. In the case of figure 1, flux is coming from main poles N. So only one magnetic pole is shown for clarity. Actually, don't think that there is only one pole in the machine. There should be an even number of poles in a machine. So minimum number of poles in a machine is 2. Otherwise it is 4, 6, 8, etc. Odd number of poles is not possible in a DC generator. If there is a one north pole, there should be one south pole. So for clarity, there is only one pole is shown in the figure. Figure 1 there is only one pole. Figure 2 there is only one pole. Figure 3 there is only one pole. So don't think that there is only one pole in a generator. There should be even number of poles in a DC generator. Minimum number of poles in a DC generator is 2. Minimum number of poles. Okay, so in the figure 1, phi 1 is coming from main poles, from north pole, main flux. Imagine there is only phi 2 in the generator. So the direction of phi 2 as in figure 2. So please note the direction. Please note the direction of phi 2. Then actually phi 1 and phi 2 are acting together. Phi 2 superimposes phi 1. And the unequal flux distribution takes place because of this armature reaction. Because armature reaction means it is the effect of armature flux on main flux. It is the effect of phi 2 on phi 1. It is the effect of phi 2 on phi 1. And the resultant flux is here represented as phi 3 in figure 3. That means the effect of armature reaction is shown in the figure 3. And unequal flux distribution takes place in figure 3. Unequal flux distribution takes place in figure 3. So what is the unequal flux distribution? So in the direction of rotation, the leading pole tip, while we are tracing the magnetic pole in the direction of rotation, first meeting point is A, that is leading pole tip is A, and second meeting point is B. So direction of rotation is shown in the figure. While we are tracing the magnetic poles in the direction of rotation, first meeting point will be A and second meeting point will be B in each pole. First meeting point is represented as, first meeting point means leading pole tip. Leading pole tip is A and trailing pole tip is B. So flux density is more at a trailing pole tip. Flux density is less at a leading pole tip. This is the effect of armature reaction. So unequal flux distribution takes place. unequal flux distribution. Due to the demagnetizing effect and cross-magnetizing effect, more flux is concentrated at a trailing pole tip B. Less flux density in the case of leading pole tip A. So more flux density at trailing pole tip B, less flux density at trailing pole tip, less flux density at leading pole tip A, more flux density at trailing pole tip B. Increase in flux density at B is less than decrease in flux density. Increase in flux density at B is less than decrease in flux density at A. So the resultant flux is decreasing. This is due to the effect of demagnetization. Anyway, demagnetizing effect takes place. Resultant flux phi 3 is less than that of phi 1. So phi 1 main flux, phi 2 disturbances the main flux. The resultant is unequal flux distribution takes place. So more flux will be at trailing pole tip B, less flux density at leading pole tip A, but increase in flux density at B is less than decrease in flux density. Increase in flux density at B is less than decrease in flux density at A. That means we can understand that due to this unequal flux distribution, the strength of main flux decreases. The strength of phi 3 is less than phi 1. So that means main flux decreases. This effect is known as demagnetizing effect. So phi 3 is less than phi 1 because of the action of the phi 2. Unequal flux distribution takes place. Flux density is more at the trailing pole tip. Flux density is less at the leading pole tip. The increase in flux density at B is less than decrease in flux density at A. Therefore, resultant flux in the armature decreases. So phi 3 is less than phi 1. The resultant flux is phi 3, which is less than phi 1. This effect is known as demagnetizing effect. So this explanation is shown in these slides. Okay, when the generator is loaded, the current flowing through the armature conductor sets up a flux denoted as phi 2 as shown in figure 2. By superimposing the main flux phi 1 and armature flux phi 2, we get the resultant flux phi 3. Referring to figure 3, it is clear that flux density at the trailing pole tip is increased, while at the leading pole tip, that means point A, is decreased. This unequal field distribution produces the following effects. Due to higher flux density at the trailing pole tip B, saturation sets in. Consequently, increase in flux at pole tip B is less than decrease in flux under pole tip A. Therefore, resultant flux phi 3 is less than main flux phi 1, known as demagnetizing effect. This will cause the reduction in generated EMF. So all those things I explained in the explained sometimes before. Okay, what about the second effect? The main flux is distorted. The main flux is distorted. From the figure itself, it is very clear. Phi 3 is totally distorted. Main flux is distorted. This distorting effect may cause sparking at the brushes. So there are two different effects. One is demagnetizing effect and other is cross-magnetizing effect. In the next class, we have to discuss what are the methods for minimizing these effects. Both are adversely affecting the DC generator. Due to demagnetization, generated EMF is decreasing. Due to cross-magnetization, sparking takes place. Flux produced by main field winding is represented as phi 1. Flux produced by armature current is phi 2. This phi 2 disturbances phi 1. So unequal flux distribution takes place. More flux density at trailing pole tip B, less flux density at leading pole tip A. So what is meant by leading pole tip and trailing pole tip? While we are tracing the magnetic pole in the direction of rotation, first meeting point is leading pole tip and the second meeting point is trailing pole tip. In figure 3, it is very clear. Flux density at B is more, flux density at leading pole tip A is less. Anyway, the increase in flux density at B is less than decrease in flux density at A. Therefore, resultant flux is decreasing. So phi 3 is less than phi 1. That effect is known as demagnetization and EMF is decreasing. From the figure, it is very clear that phi 1 is totally disturbed and it is represented as phi 3. So phi 3 is a totally disturbed flux. Phi 3 is less than phi 1. Due to cross magnetization, the main flux is totally distorted. Due to this total distortion, sparking may produce at the brushes. Thus there are two different effects, demagnetizing effect and cross magnetizing effect. I think this topic is very clear. So armature reaction means it is the effect of armature flux on main flux. It is the effect of armature flux on main flux. It has two different effects, demagnetizing effect and cross magnetizing effect.